All right, 4.7 graphs of rational functions. I started recording this a second ago, and then I had to stop. So anyway, so I'm starting over, but I've already drawn a little bit down here. But anyway, we're ready to graph rational functions. There's a little bit of analysis we have left to do. One of the things that we need to realize is that the graph of a function can never cross a vertical asymptote. So what I've drawn here is just an x and y axis and then a vertical asymptote, and then I started drawing this curve, which was supposed to represent a function. Now, you know that a function can never cross a vertical asymptote because the vertical asymptote is telling us that at some point the graph is going to start getting closer and closer to this line. If it crossed over it, even if it got closer and closer, let's say down here, like that or something, this would not be a function because it would fail the vertical line test, right? So remember, functions have to pass the vertical line test. This would fail the vertical line test. Or maybe it doesn't do that. Maybe it kind of goes off in this direction down there, but then up here it would have to, at some point, swing back around and start getting closer and closer to the vertical asymptote, in which case it would fail the vertical line test there, right? So a function can never cross a vertical asymptote. However, a function could cross a horizontal or an oblique asymptote, right? So, for example, let's say you've got a horizontal asymptote. You could have a function that crosses this thing and then starts to get closer and closer to it eventually. This doesn't fail the vertical line test, right? This is a function. There's no problem with this, okay? And the same thing if you had an oblique asymptote. Right? So if you had some kind of oblique asymptote, you could easily have a function that does something like this or whatever, and that would be perfectly fine. It's not failing the vertical line test when it does that. So anyway, so a graph can cross a horizontal or an oblique asymptote. It just can't cross a vertical one. So if we want to graph a rational function, then one thing we're going to need to be able to do is decide whether or not the function crosses its horizontal or oblique asymptote. So to that end, suppose that f of x is a rational function that has some horizontal or oblique asymptote a of x. If the graph of f crosses a of x, let's say at x equals c, then it must be the case that f of c equals a of c. So to find out if a graph crosses its asymptote, we solve f of x equals a of x for x. Okay, and if we get no solution or whatever, then that tells us that okay, the graph never crosses its asymptote. If we do get a solution though, then that tells us that the graph will cross its asymptote and where that happens. So let's practice this, right? So it says determine if the following rational functions cross their horizontal or oblique asymptotes. If so, find the point where it crosses. So the first thing we would need to do in order to determine that is to determine what the horizontal or oblique asymptote is. In this case, we've got a horizontal asymptote at 1, right? The degrees of the numerator and denominator match, so it has a horizontal asymptote at the ratio of the leading coefficients, which would be 1 over 1 or just 1, right? So its horizontal asymptote, we know just by looking at it, is y equals 1. So what we want to do to determine if this thing crosses its horizontal asymptote is we're going to set the function equal to the asymptote and then solve for x. So we're going to say x squared plus 2 over x squared plus x minus 2 equals 1, and then solve for x, or at least try to solve for x. Maybe it's not solvable, in which case that tells us that the graph doesn't cross its asymptote. But let's try. So I would multiply both sides by this denominator to clear the fraction, and then solve for x. So I want to move everything over to one side since these are quadratic equations, except that look, when I do that, the x squareds will cancel. So actually this turns out to be a linear equation. I can just move the 2 over here and get 4 equals x. Ooh, interesting. So that tells us that this function crosses its horizontal asymptote when x is 4. Okay, so that's interesting. So yes. f crosses its horizontal asymptote at the point 4, and of course y is 1, right? Y is 1, that's what we set it up as. So it crosses its horizontal asymptote at the point 4, 1. One thing that just occurred to me that we may need to check for is that you may solve this and get, x equals something, but if that value makes the denominator of your rational function equal to 0, then that tells you that actually your function isn't crossing its horizontal asymptote there. What's happening is that you have either a hole or an asymptote, right? A vertical asymptote going on at that point. But that's not what we have in this case. 4 does not make the denominator 0, right? 4 is not a 0 of the denominator. So yeah, this is definitely going to cross its horizontal asymptote at 4, 1. Let's do another. Okay. So another case where we've got a horizontal asymptote. This time the horizontal asymptote is at 2, right? Because the degrees match, so the asymptote is the ratio of the leading coefficients, right? So we know that the horizontal asymptote in this case is y equals 2 over 1, which is just 2. So to see if this crosses that horizontal asymptote, we would set 2x squared plus 2 over x squared minus 4 equal to the horizontal asymptote 2, and then try to solve for x. So multiplying both sides by x squared minus 4, I get 2x squared minus 8, right, when I multiply by 2. And this is one where clearly, right, we tried to move the 2x squared over, but it just cancels with the one on the other side, right? And so we get the statement 2 equals negative 8, which is not true, right? So we would say f does not cross its horizontal asymptote in this case, right? Okay, let's look at another one. So f of x equals x cubed and some change over x squared and some change. What I'm noticing is that the numerator, the degree of the numerator, is greater than the degree of the denominator. So that tells me that I don't have a horizontal asymptote, I actually have an oblique asymptote. And since the degrees are different by just 1, the oblique asymptote that I have here is going to be linear. To find the oblique asymptote, I've got to do some long division. So let's do x squared plus 2x plus 5 into x cubed plus 3x squared plus 2x minus 5. X squared is going to go into x cubed x times, right? Oh, I should put that here, x times. We get x cubed plus 2x squared plus 5x. And then we're going to subtract x squared minus 3x and bring down the 5, negative 5. Did I do that right? 2x minus 5, yeah, negative 3x. Okay, x squared goes into x squared once. So this is x squared plus 2x plus 5. We subtract. We get negative 5x minus 10. Okay? So in reality, we can say f of x is x plus 1. I'm actually going to say minus and factor out the negative, so I'm going to say minus 5x plus 10 over x squared plus 2x plus 5. If you're confused about that, I mean, don't worry. You could have said plus negative 5x minus 10. It would still be the same thing. What's really important, though, is this. This is our oblique asymptote, right? So that's our oblique asymptote. So to see if f crosses its oblique asymptote, we're going to set this function equal to this asymptote and then solve for x. Ooh, what have I gotten myself into? X cubed plus 3x squared plus 2x minus 5. I'm just going to pretend, right? So we would say over x squared plus 2x plus 5 equals x plus 1. But we know that we're going to multiply both sides by x squared plus 2x plus 5, right? So I'm just going to say this equals x plus 1 times x squared plus 2x plus 5 to try to solve this thing. We've got x cubed plus 3x squared plus 2x minus 5. Isn't it nice to know that you're well equipped to handle these kinds of equations? I mean, you know the general strategy is going to be multiply this out, move everything over, factor. And even if you have a cubic at the end of the day, you can factor this thing. You've got rational zeros theorem, you've got all kinds of good tools. Well, let's see. Let's multiply it so we get x cubed. I don't think we're going to have an x cubed once we move everything over. 2x squared plus x squared will give me 3x squared. I'm sorry, I'm kind of condensing this because I'm going to run out of room if I don't. Then I'm going to have a 5x and a 2x, which will give me 7x. And then I'm going to have a 5. Okay. Ooh, okay, so the x cubes cancel, but so do the 3x squareds. That's kind of nice. I'm going to move this 7x over there and this 5 over there. So moving this 7x over, I would get negative 5x equals, moving this 5 over, I would get 10. And then dividing through by 5, I would get x equals negative 2. So it seems like this function is going to cross let me try again. This function is going to cross its oblique asymptote when x is negative 2. Now I wonder, is negative 2 a 0 here? We would get 4 minus 4 is 0 plus 5 is 5. So no, negative 2 is not a 0. So, so yeah, the function definitely crosses its oblique asymptote at negative 2. So f crosses its oblique asymptote at the point. Ooh, well, I wonder. If we plug in negative 2 here, negative 2 plus 1 is negative 1, so it crosses at negative 2, negative 1, right? I plugged in negative 2 to the oblique asymptote. I guess, actually, the function values are the same, so you could have plugged it in here as well. You should still get negative 1. I'm not going to do all that work. Oh, maybe I will, because I've already plugged in negative 2. I know that in the denominator I get 5, right? In the numerator I would get negative 8. Plus 12 is 4. Minus 4 is 0. Minus 5 is negative 5. So I get negative 5 over 5, which is sure enough negative 1, right? So either way, you can plug it in here or plug it into the oblique asymptote. Since it's crossing the oblique asymptote at negative 2, the output values should be the same, right? Anyway, so that's that one. Let's do another one. Okay, so another oblique asymptote here, since the degree of the numerator is greater than the degree of the denominator. I could actually just do synthetic division here. The corresponding 0 would be negative 1, right? And I have x squared plus 0x minus 4. So 1, negative 1, negative 1, 1, and negative 3. So f of x is really, how does this work? F of x is is really divided by, so it's really x squared minus, x minus 1. Wow, why am I having such a hard time? It's x minus 1 minus 3 over x plus 1. Man, that was way more difficult than it needed to be for me. I must be tired or something. Anyway, there we go. So there's our oblique asymptote, right? X minus 1 is our oblique asymptote. We want to know if f crosses its oblique asymptote, so we're going to set x squared minus 4 over x plus 1 equal to x minus 1. So I know that in order to solve that, I'm going to multiply both sides by x plus 1, right? I get x squared minus 4 equals x squared minus 1, and this thing's not going to cross, right? We get negative 4 equals negative 1. F does not cross its oblique asymptote. Okay, and there's that. So so that's that one. So we saw a couple examples of horizontal asymptotes, a couple of examples of oblique asymptotes, and I think we saw one of each, right, where f does cross and where it doesn't cross. So you kind of know how this works. One thing that we didn't do is we didn't look at the case when the degree of the denominator is greater than the degree of the numerator, because remember, in that case, that means that the horizontal asymptote is at y equals 0. The reason that it's not even really all that important to look at that case is because if the horizontal asymptote is y equals 0 and the function crosses its horizontal asymptote, that's the same thing as finding the x-intercepts of the graph, which we would have already done at this point anyway. So if your horizontal asymptote is at y equals 0, then there's no additional work for you to do. You already know if it's going to cross its asymptote if it has x-intercepts. What am I saying here? Then determining whether it has the same, yeah, right? Because yeah, so just to give you a picture of that, right? If you've got a horizontal asymptote at y equals 0 and the graph crosses, the graph has an x-intercept, let's say right there, well then you already know that it crosses its horizontal asymptote, right? You've already done that. So there's no additional work to be done in that case. So now with that in mind, I think we are officially ready to graph some rational functions. Okay, so to graph a rational function, first of all, we're going to find all holes, asymptotes, and intercepts and graph those things. And then we're going to determine if and where the graph crosses its horizontal or oblique asymptote. And then once we've done that, we've got really good framework for graphing our function. We could pretty much we could almost graph the function just based on that information alone. But sometimes we need a little bit more information. So what we'll do is plug in a test point in each of the regions created by the vertical asymptotes to determine where the graph is above and where it is below the horizontal or oblique asymptote. Okay, so we might need to do that in certain cases. So let me walk you through several examples of this. So number 2 here says we'll graph the function, of course. So we're going to start off by finding holes, asymptotes, intercepts. Okay. To do that, I'm going to factor everything. This is x plus 1 over x plus 3 times x minus 3. And so I can tell right away that I have an x-intercept at -1. And that I have vertical asymptotes at -3 and +3. I don't have any holes. And since the degree of the denominator is greater than the degree of the numerator, I know that I have a horizontal asymptote at 0. So let me write this stuff down, right? So my x-intercept, in this case I only have 1. That's the point -1, 0, right? That comes from the 0 in the numerator. My vertical asymptotes are at x equals -3 and at x equals +3. No holes, right? So I can say, I mean, you don't have to write this out, I guess, but just to make sure that we're checking all of that we're checking off all the boxes, right? X-intercepts, vertical asymptotes, no holes, and then I have a horizontal asymptote at y equals 0. Okay, so that's all the information I have. Let me put it on the graph. So I've got a vertical asymptote at -3 and another one at +3. And then I've got a horizontal asymptote at 0. That was kind of ugly. And I have an x-intercept at -1, 0. So definitely this graph crosses its horizontal asymptote, right? This is one of those cases where we don't need to check if the graph crosses its horizontal asymptote because the horizontal asymptote is on the x-axis, and so we already know that it crosses the x-axis at -1. In fact, something that I haven't mentioned but that is, I think, fairly intuitive is that the rule for multiplicities about whether or not the graph crosses or just touches only is the same for rational functions as it is for polynomial functions, right? So like our 0 here of -1, it's a 0 of multiplicity 1. that means that the graph is actually going to cross through this point. It's not just going to, you know, touch it and then come back down. It's actually going to cross through because it's an odd multiplicity, right? If it had an even multiplicity, like if you had x plus 1 times x plus 1 in the numerator, then it would only touch and then come back down. I might show you this in Desmos just to kind of verify it. Another thing that might come in handy, I mean, I got my x-intercept. Maybe a y-intercept might be nice. Y-intercepts, you don't always have them. I mean, if you had a vertical asymptote at 0, then you wouldn't have a y-intercept. But in this case, we don't have a vertical asymptote at 0, which means we must have a y-intercept somewhere. You find your y-intercept, of course, by plugging in 0 for x. And if we do that, we get 1 over 3 times negative 3. So 1 over negative 6, or negative 9. Wow. So negative 1/9. So the y-intercept is at the point 0, negative 1/9. Oh, that's really tiny. It's like right here. 0, negative 1/9. But that does give you some useful information because you know that the graph is going to cross through this point and then it's going to come up here. That means on this side it must be going down. And remember, it can't cross this vertical asymptote, so it must look something like that. And then on the other side, it can't come back down this way because that would require it to cross the x-axis again. And you only have one x-intercept. So you know that it's not going to come back down and cross the x-axis again. It must come up like that, right? So the graph must look something along those lines. Now the question is, what's going on over here and what's going on over here? So to find that out, we're just going to plug in some test points. Like I'm going to plug in negative 4 to see if the graph is above or below this horizontal asymptote. And the same thing over here, I'm going to plug in positive 4 to see if I'm above or below the horizontal asymptote. So, so if I plug in negative 4, f of negative 4, that's negative 4 plus 1 over negative 4 plus 3 times negative 4 minus 3. That's negative 3 over negative 4 plus 3 is negative 1. Negative 4 minus 3 is negative 7. So negative 1 times negative 7 is positive 7. So this is a negative 3/7. So I'm definitely below the horizontal asymptote there. And since I know that this graph doesn't ever cross the horizontal asymptote again because there are no other x-intercepts, it must be trapped in here like that. Okay? And then I can do the same thing over here. Figure out if I'm above or below. So I'm going to plug in 4 to see where I'm at on that side. Get 4 plus 1 over 4 plus 3 times 4 minus 3. That would be 5 over 7 times 1, 7. So 5/7. So over here I'm above. I'm at 5/7, right? So that tells me it must look something like this on the right-hand side of the graph. Okay, so there's the picture that we get. Now I'm curious to know how this stacks up with what you would get in Desmos. So let's open up Desmos. So we had x plus 1 over x squared minus 9. What? I got this curve wrong. I got this curve going the wrong way. Now I wonder how that happened. Let me take a look. You see how I got this curve going the wrong way? It should be, according to Desmos, it should be going the other way. That tells me I must have gotten this point wrong. Oh, yeah, I didn't get the point wrong. I just graphed it wrong like an idiot. You know, sometimes I do stupid things. That's okay. All right. Well, so I should have known better. Again, this is one of those instances where you're probably screaming at your computer screen like, "Why did you put the point there when it was 0, negative 1/9?" And you were right. You were right. I was wrong. I apologize. Okay, so it wasn't this thing. You know, this also provides a good moral to the story that you really shouldn't use pen. You really shouldn't use pen. Okay, we're going to cross the x-axis there and then hit the y-intercept there. Should look like that. Wow. Well, I'm glad I checked it in Desmos. That would have been embarrassing. There you go. Well, it is embarrassing. I'm embarrassed. But somehow, if we were in person, if we were in class, I would find a way to blame you. But there we go. All right, so that's that one. Now it looks like what Desmos has. But I wanted to show you something else. So remember what I was saying about multiplicity. So if I had x plus 1 times x plus 1, so if it had a multiplicity 2, see that? So now instead of crossing through at that point, it just comes up, kisses that point, and then comes back down, right? It also affects what happens on the left and right hand sides as well, but that's kind of interesting, right? Oh, why is it giving me errors now? Because I have an exponent that I never filled in, but I don't want to have an exponent. There we go. Okay, so that's that one. All right, let's look at the next one. Hopefully I don't make any stupid mistakes like that again. Oh, and I better go quicker. We've got how many more? 1, 2, 3, 4, 5 more to look at. So I better move a little bit more quickly. X squared minus 9 over x plus 3. Okay, this is x plus 3 times x minus 3 over x plus 3. So I get a bunch of information here. For one thing, I know that I have a hole at negative 3. And then I also know that I have an x-intercept at positive 3. So I'm going to write down x-intercept at 3, 0. Hole at negative 3. What would the y-coordinate of my hole be? Well, if I canceled off the common factor, then I would get x minus 3 as my leftover. And if I plug in negative 3 there, negative 3 minus 3 is negative 6. So I must have a hole at negative 3, negative 6. I don't have any vertical asymptotes, right? The only 0 from my denominator was actually a hole. So I don't have any vertical asymptotes. I don't have a horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. But that does tell me that I've got an oblique asymptote. And in this case, I've already kind of done the division because if we divide x squared minus 9 by x plus 3, well, the x plus 3's cancel. You're left with x minus 3. So the oblique asymptote is y equals x minus 3. I could ask myself, whether or not this graph crosses its oblique asymptote. Do I need to do that, or can I get out of doing that work? Well, let's just do it. It's going to be quick, right? So to figure out if the graph crosses its oblique asymptote, we're going to set f of x equal to the oblique asymptote. When we multiply both sides by x plus 3, we're going to get x squared minus 9 equals x squared minus 9. Ooh, that's interesting. We get 0 equals 0. That means there are infinitely many solutions. So I just realized what's actually going to happen here. That this function is just going to look like a straight line, isn't it? Because when you cancel these things, you just get x minus 3, right? As long as x is not equal to negative 3. So you just get this straight line. So what we're discovering here is that yes, this function crosses its oblique asymptote everywhere, right? At infinitely many points. So it crosses it for every value of x, which makes sense, because its oblique asymptote is just this straight line. Well, let's graph this thing. So this is just a straight line. I've got an x-intercept at 3, 0. I've got a hole at negative 3, negative 6, 2, 3, 4, 5, 6. I know that my y-intercept is going to be 0, negative 3. And then otherwise, this is just a straight line, no vertical asymptotes. This is my oblique asymptote, and it happens to be what my function looks like. Okay, so very interesting. So that's that one. It's just a straight line with a hole. Okay. Should we look in Desmos? Make sure that I'm not leading us astray, as I have so often done recently. Let's see. X squared minus 9 over x plus 3. There you go. Yep. So just a straight line, and we should have a hole at -3. Yep. Okay. Good, good. Moving on. (2x squared minus 1 over 2x squared plus x minus 3). Can we even factor these things? Yeah, as a difference of squares. We can factor the numerator as a difference of squares. It would have to be root 2x plus 1 times root 2x minus 1. Right? Because then you would get 2x minus 2 root x plus 2 root x would cancel, and then minus 1. Right? So 2x squared, I should say, when you do the firsts. Denominator, will this thing factor? I think so. I think we can get it. I must have a 3 here and a 1 there in order to get this 1 in the middle. Now what do the signs have to be? This one needs to be positive. This one needs to be negative. And there you go. Okay, so there's the factorization. So what do we discover here? We discover we've got x-intercepts at the points. Well, if I solve this for x, I would subtract 1 and then divide by root 2. So that would be negative 1 over root 2. Or if you like rationalizing, it would be negative root 2 over 2, right? And this one's going to be positive root 2 over 2. 0. Root 2 over 2 is like 0.7-ish. So these x-intercepts are going to be at 0.7 and negative 0.7 respectively. We know that we've got no holes, okay, because none of the zeros in the denominator are going to cancel with anything in the numerator. But we do have a couple vertical asymptotes, right? One of the vertical asymptotes, if I solve this for 0, I would subtract 3, then divide by 2. So I get negative 3 halves, right? So I've got a vertical asymptote at negative 3 halves and at 1. Okay, what about horizontal or oblique asymptotes? It looks like since the degrees are the same, I'm going to have a horizontal asymptote at the ratio of the leading coefficients. So my horizontal asymptote, in this case, is going to be y equals 2 over 2, right? 2 over 2, which is 1. Finally, let's decide if this graph ever crosses its horizontal asymptote. So I'm going to set 2x squared minus 1 over 2x squared plus x minus 3 equal to 1. In order to solve that, now I'm going to have to multiply both sides by 2x squared plus x minus 3, and 1 times that is just that, right? So I'm skipping a step, because if I don't, I think I'll run out of room. Okay, 2x squared will cancel. I can move this 3 over there and get 2 equals x. Ooh, interesting. So this graph is going to cross its horizontal asymptote at the point 2, 1, right? So f crosses HA at 2, 1. Okay, all good information. Let's get it on there. Let's get it on the graph. So x-intercepts at 0.7 and negative 0.7. Then I've got vertical asymptotes at negative 3 halves. So 1 and 1.5, so negative 3 halves there. And at 1, ooh, this is just tight quarters over here. Okay. Horizontal asymptote at 1. And the graph crosses its horizontal asymptote at 2, 1, right there. What a mystery. Okay, I'm pretty sure that here in the middle it's going to have to look something like this, because we know that the graph doesn't cross its horizontal asymptote here in the middle, but it does have these two x-intercepts. So and those intercepts are degree 1, or multiplicity 1 rather, And so we know that the graph is going to completely cross through at those 2 points. So it must be doing something like this. Okay. We could figure out the y-intercept, right? If we plug in 0 for x, we get -1 over -3, so that's 1/3, right? So the y-intercept is at 0, 1/3, right? So yeah, so it's got to look something like that, okay? What's happening over here? This horizontal asymptote is the end behavior of the function. So definitely this function is going to get closer and closer to 1 as we move out. The question is, does the function come up this way and then start to curve toward the horizontal asymptote, or does it come down this way, cross, and then come back up? I think it's got to come from up above and not down below, because if it came from down below, it would have to cross the x-axis somewhere, and we know that we don't have any x-intercepts over here. So it must come down from up above, cross through right there, and then it's not allowed to hit the x-axis over here, right? No x-intercepts, so then it starts to come back up like that. So that's what it must look like on the right-hand side. What does it look like on the left-hand side? Well, same reasoning, right? We know that it can't be trapped down here because that would require it to cross the x-axis somewhere, and we know that we don't have any x-intercepts. So it must be trapped up here in this quadrant. So I'm not even going to use test points. I'm fairly confident that that's what that looks like. Let's check it in Desmos. Let's take a look. 2x squared minus 1 over 2x squared plus x minus 3. Haha. Yep. Looks just like what I did, right? In fact, I'm going to put the horizontal asymptote on there, y equals 1, so that you can see, yeah, see it's crossing right there at 2, just like we thought. But then it starts to get closer and closer to the asymptote. It never crosses it again, you know? Anyway, so that's that. Kind of interesting. Okay. See, rational functions I think are fun. I think they're a lot of fun to graph, right? The way that we can kind of figure them out. Okay, 3 more. X plus 1 over x cubed plus x squared minus 4x minus 1. Oh, that thing can be graphed by or factored by grouping. If I ever saw a factoring by grouping, this was it. In fact, I think we've done this before, right? Because now we're going to factor out the x plus 1. We'll be left with x squared minus 4. And x squared minus 4 is a difference of squares that can be factored as x plus 2, x minus 2, right? So we've got x plus 1 over x plus 1 times x plus 2 times x minus 2. Okay, so all kinds of information here. We know that we've got a whole at -1. What's the y-coordinate? Well, if I canceled those and then plugged in -1, I'd have 1 over 1 times -3. So -1/3, right? So I've got a whole at -1/3. -1, -1/3. Okay. I have no x-intercepts. Right? Because the only candidate was actually a whole, not an x-intercept. So no x-intercepts. I've got a couple of vertical asymptotes. One at -2, one at +2. What else? What about horizontal asymptotes? Well, so the degree of the denominator is greater than the degree of the numerator. So I've got a horizontal asymptote at 0. And I don't need to ask myself whether or not the function crosses its horizontal asymptote. I already know. It doesn't, okay? Because if it did, then I would have an x-intercept, and I don't, right? I don't have any x-intercepts. So that takes care of that. Anything else I need? I mean, a Y-intercept might be nice if I plugged in 0 for x. If I plug in 0 for x, I get 1 over negative 4. So negative 1/4 is my Y-intercept. Let's start to put this stuff on here. So I've got vertical asymptotes here and here. A horizontal asymptote here. No X-intercepts. A Y-intercept at 0, negative 1/4. And a hole at negative 1, negative 1/3. So maybe there. Right? So a hole right there. Okay, very interesting. So I'm sure that this thing looks like this, okay, because the function never crosses the x-axis. I'm not sure what's happening in these two places, so I'm going to have to plug in test points for that. I think I'll plug in negative 3 and positive 3 to see what's happening on the other sides. So f of negative 3. It's easier for me to plug it into the factors form. It's just easier to do the math for some reason. So if I plug in negative 3, I'm going to get negative 2. I say it's easier to do the math, and then I stumble. I get negative 2 times negative 1 times negative 5. Okay, so this is 1/5, right? It would be negative 2 over negative 10, so positive 1/5. Okay, so at negative 3, I'm at positive 1/5. All right, so that must look like that. What about at positive 3? I would have 4 over 4 times 5 times 1. That's 4/20. 4/20, which is again 1/5. Oh, very interesting. 1/5. I think there's some symmetry going on here, right? Like once you cancel this off, you've definitely got some interesting symmetry. So that must look like that. Okay, I'm not going to check it in Desmos. You're welcome to check it on your own, but I think that's how that one would look for sure. Let's do part E. 4x squared plus 4 over x squared plus 4. Well, you know, neither of these things is going to have any real zeros. The zeros of the denominator are plus or minus 2i. So if you wanted to call them vertical asymptotes, they would be imaginary vertical asymptotes. They're not going to show up in the graph, right? So you don't have any vertical asymptotes. You don't have any x-intercepts, right? Same reason. The x-intercepts will be at plus or minus I, which doesn't really help us if we're trying to graph something in the real coordinate plane. So let's write down this stuff. So x-intercepts, none. Vertical asymptotes, none. Holes, none. Right? You don't have any real zeros in either the numerator or denominator. There's no hope you're going to cancel. Well, in fact, if you did find the zeros, they wouldn't cancel anyway. So no holes. Goodness. So no good information. Well, what about we've got a horizontal asymptote at 4, right? Does the graph cross its horizontal asymptote? Let's see. So if I set the function equal to its horizontal asymptote, then I get 4x squared plus 4 equals, when I multiply this, I'm going to get 4x squared plus 16. Ooh, so that says 4 equals 16. So f doesn't cross its horizontal asymptote. Oh, this is interesting. So f doesn't cross this. Well, okay, so let's put what we have on there. We know that it's got a horizontal asymptote at 4. And that's all we know. Well, that's not all we know. We also know that it doesn't cross this horizontal asymptote and that it doesn't cross the x-axis. So so those are good pieces of information to have on hand. Maybe we could get a y-intercept. Y-intercept. If I plug in 0 for x, I get 4 over 4, which is 1. So the y-intercept is at 0, 1. It doesn't cross the x-axis, which means it can't dip down below the x-axis. It also can't get above the y-axis. So what's going on? Remember, the horizontal asymptote is the end behavior of this graph. So I'm thinking that the function must look something like that. That's the only thing that makes sense. You could plug in a couple test points to sort of verify that this is the way it looks, but that's got to be how it looks. Okay, let's check in Desmos. Yeah, yep, that's what it's looking like. And we have y equals 4 as our horizontal asymptote. So there you go, right? So that's that one. And I think I've got one more. This last one better be an example where we've got an oblique asymptote, because we haven't really seen any good example of that. Yeah. Yep. See, I know myself too well. Well, let's do this. We just factored this thing, so I'm not going to redo the work. I already know that it looks like x plus 1 times x plus 2 times x minus 2. In the denominator, I can factor out the x, and I'm left with x plus 1. So there's the factorization. I've got all kinds of good stuff happening here. We've got a whole at -1. If we were to cancel off that factor and plug in -1, we would get 1 times -3 over -1. So that's -3 over -1 is +3. So we've got a whole at -1, 3. Good. We've got a vertical asymptote at 0, right? At x equals 0. Right? Because that comes from this factor in the denominator. Okay. We've also got a couple X-intercepts at -2, 0 and at 2, 0. Let's get the Y-intercept while we're thinking about. Actually, we don't have a Y-intercept, right? If you plug in 0 for x, you're going to get -4 over 0, which is undefined. So that's interesting to note. There's no one. Oh, well, that makes sense, right? We have a vertical asymptote at 0. So the graph can't cross the y-axis, because graphs, a function can't cross a vertical asymptote. Okay, well, so there you go. Now, we've got an oblique asymptote, right? Degree of the numerator is greater than the degree of the denominator. To figure out where the oblique asymptote is, we're going to have to do some long division. So let's do x squared plus x plus 0 into x cubed plus x squared minus 4x minus 4. I would multiply by x to get x cubed. And subtract x cubed plus x squared. So yeah, those are gone. Well, so I'd get a 0x squared minus 4x minus 4 This is so bizarre. Well, but whatever. So how many times would what would I multiply x squared by to get 0x squared? And well, the answer would be 0, right? 0x squared plus 0x plus 0. We subtract, and of course we're going to get negative 4x minus 4. Okay, so in other words, f of x is really x plus negative 4x minus 4 over x squared plus x. Okay, so that tells us that our oblique asymptote is x. Now, this is all good information. There's one more piece of information I need to know. I need to know if f will cross its oblique asymptote. So does f cross its oblique asymptote? Let's see. We're going to do x cubed plus x squared minus 4x minus 4 over x squared plus x equals x. And then solve for x, right? So we would get x cubed plus x squared minus 4x minus 4 equals x cubed plus x squared. Those are going to cancel. We get negative 4x equals 4 if I move the 4 over, so x is negative 1. So we're being told that the graph will cross its oblique asymptote at negative 1, but we're also being told that that's actually a hole. That's actually a hole in the function. So I'm not exactly sure what to make of that yet. I think it'll all make more sense when I start to graph stuff. So let's do it. We've got a vertical asymptote at x equals 0. And I've got oblique asymptote at y equals x. So that would be that straight line right there. Okay, so there's my vertical asymptote, my oblique asymptote. I've got x-intercepts at 2, 0 and at negative 2, 0. I've got this weird hole thing at negative 1, 3. I'm not exactly sure what to make of that yet, so I'm not going to try to graph negative 1, 3. I'm not sure really what's going on with that. Okay, and I think that's all the information I have. But this is good information. The graph can't cross the y-axis. It also can't cross the oblique asymptote, except possibly at negative 1. But so consequently, I know that at least on the right-hand side, the function has to look something like that. Something like that. On the left-hand side, if the graph crosses its oblique asymptote at negative 1, then it's possible it could be going downward. And then maybe, I don't know, it would have to just touch there and come back down, because it does, the end behavior has to be this oblique asymptote, so it would have to come back down. In other words, it can't just go up forever. It would have to come back down. And since this X-intercept was a multiplicity 1, I don't think that it's just going to kiss and come back down. I think if it crosses, it has to cross through, which leads me to believe that the function is not going to cross its oblique asymptote there. I think it really does have a hole at negative 1, 1, 2, 3. I think really this is what's happening, right? So I think it's really doing this thing. Now, I'm like 99% confident this is the way it looks. Otherwise, I wouldn't have drawn it in pen. But if I wanted to be extra certain, I mean, I could plug in something. I could plug in like negative 1/2 and make sure that I really am up here somewhere, right? If I plugged in negative 1/2, I'd have 1/2 times 3/2 times negative 5/2 in the numerator, and in the denominator I'd have I said negative 1/2, right? So I'd have negative 1/2 times 1/2. So I'd have negative 1/4 in the denominator. In the numerator, I'd have negative 15/8. The negative and the negative will cancel and leave a positive, right? If I flip and multiply, then the 8 will cancel 4 and leave a 2. So I get 15/2. So that's like 7.5, right? So negative 1, 7.5, right? It's adding up. So I think this is definitely what's happening. Let's take a look at Desmos. Since this is the last one, we might as well. So we've got x cubed plus x squared minus 4x minus 4 over x squared plus x. Yep, that's what it's looking like. And we've got this whole at negative 1. Yep. So there you go. That's it. That'll do it for this section.